Okay, in this section, we're going to be talking about the concept of a function, and we're on section 2.3, all about functions. You may have heard me even mention it in earlier sections, but this is where it officially shows up. If something is a function, it's a special type of relation in which no x value is ever repeated. Later, we'll study something called a one-to-one function, and in it, not the x nor the y can be repeated, but for regular, just a function to get the okay, the check mark that it is a function, and then we can use the f of x notation. Only the x value is what we focus on. Only the x value is not repeated. Now we have lots of functions, mainly what we study. Lots of function examples. We've been talking about maybe the line. You've noticed it is a function. Y equals, say, 2x plus 3. That is going to be a function. No matter what I plug in for x, you get a unique value for y. There's never two different answers for the same x. For example, if I plug in 1, 2 times 1 is 2, plus 3 is 5. If I plug in -1, 2 times -1 is -2, plus 3 is 1. Let's see. If I plug in 0, 2 times 0 is 0, plus 3 is 3. 7, just for some sample points. I won't do this forever, but you could do it forever is the point with linear equations. You could just keep plugging in numbers for x, spitting out unique values for y. This x value never gives you two different answers. And you might be wondering, well, when would that happen? And I will be showing you some examples of that. But in general, for most of the things we study, we will be studying a lot of functions. We have a lot of examples of those. So plugging in for x, multiplying by 2 and adding 3, getting a unique value each time on this problem. And then whenever we graph these, also we'll see that there's a uniqueness about it that way as well. Over 1 up 5, back 1 up 1, 0, 3. I didn't finish this. Let's do that. 2 times 7 is 14. 14 plus 3 is 17. Oh, maybe I don't want to graph that. It's up here. So, but you can tell enough now to see that is a linear equation. Linear equations are always functions. And there's never going to be a repeated x value. There's no 1x. Like if I plug in 1, I get an answer. There's some equations where you plug in for x and there's two possibilities for y. So the x value gets repeated. Never happens in a linear equation. Also, we can use the vertical line test. If you can draw a vertical line and you only touch the graph in one place, that also verifies that this is a function. Now, if something makes the cut, we can say, yes, no x is ever going to be repeated in this. Then we can start calling it f of x equals. That's the function notation. And you'll start seeing this starting in section 2.3. Instead of saying y equals, it'll be f of x equals. So this is just a notation that means the same thing as y. They're interchangeable, but it tells you, hey, this meets the function definition where no x is ever repeated. Every time you plug in for x, you get one unique answer for y. All right, and then x, f of x, means x is the variable in use. So it wouldn't always have to be an x. For example, which it is, x is the default. And you know, we use x a lot in algebra. But say we're doing a problem that uses t for time. If it's like we saw in chapter 1, some of the applications, they'll use some different letters if it means something in the problem, like t shows up for time a lot. So if we were doing, and we could even say g of t equals -16 t squared plus 27t minus 3. There would be an example. It doesn't always have to be f. It could be a function g. We use f, g, h a lot, it seems like, in this section. But it could be any letter. It could be any letter of the alphabet. That's the name of the function. So this is function g. And in terms of t, that's the input variable, the domain variable, what we normally have for x in our problem. Again, sometimes we change it up when it has a reason to for an application. All right, so that's kind of the overview. You can see the official definition if you're on your handout is as a function is a special relation with a correspondence between the first set, which we normally call the domain, and the second set called the range, such that each member of the domain corresponds to exactly one member of the range. This is the more official definition, and it's just saying that X is not repeated. Another word for a correspondence is a relationship. Like another example, maybe a more real-time example to you would be like every ACTC student has a student ID, and that's a relationship. We have the student, we have the ID. And then even if we did that backwards, every student ID goes to exactly one student. That's actually a one-to-one relationship. It would even go above and beyond the regular function tests. Another example I have here on your handout is where West Virginia has two different senators. You know, in the states we have two, so we have one domain value like the state going to two different answers for Y. So that would be not a function relationship. It's a fine relationship, but it's just not a function relationship. When you have one domain value, which can mean, you know, X in general, but it could be something in real life like a state, the name of a state. So a name of the state corresponding to two different values, in this case, senators. So one X value corresponding to two Y values, that would be not a function relationship. Then, moving on in your notes, we'll go back into the next page talking about domain and range. So I've mentioned those words. Let's talk about those a little deeper. Domain means a lot of things, and I mean, it means the X values, but we talk about it in different ways. So I want to try to hit some thoughts on the domain. In general, it means the X values. If you're doing like a simple little equation, a linear equation, we'll say, and we're inputting for X. We input a number for X, times it by 2, add 3, outputs a Y value. We consider the range to be the Y values, the output values. So normally when it's in function notation form, when we've got it solved for Y, and also that's a good way to use your graphing calculator. If you're using a graphing calculator, you want to solve for Y first anyway, to input it. When it's in this form, you're probably inputting for X, although you're always welcome to input on the Y side and solve for X. That's still, you know, okay. But generally, if it's solved for Y, it's just so much easier to plug in for X, do whatever operations are over on that side. So we consider normally the X values as the input or the independent variable. The independent variable. The input variable, it's kind of driving it. You plug it in independently to X. You do these operations, and then Y is kind of at its mercy, I say. It's the dependent variable of whatever happens over there. Depends on what happens over there. So it's the dependent variable. The answers you get for Y are considered the output or the dependent variables. So domain, also you can think of it whenever we graph this as how wide it gets. The domain is also the wideness. How far does it go left to how far does it go to the right? So how wide does the graph get? You know, whenever we're graphing, X is left to right, the horizontal graph, and Y is the vertical. So the range is the vertical values. Or also would be considered the how low to how high, the low to high, where this is the left to right, the X. And maybe that just makes sense anyway, you'd know that, but we'll be looking at that a lot with every graph. We're like, what is the domain of this? What is the range of this? Now on this, the linear equation, it's a friendly graph. I say it's like the friendly line reference. So it's friendly graph, everything's okay to input for X, and then you get all different values for Y. There's never a restriction on what the answers could be. And you might again be thinking, well, what kind of restrictions? And we will see some graphs that have restrictions. But here, everything goes. We plug in for X, multiply, and then add 3. We get some values, plot those solutions, and then connecting your dots, the graph of our line. So it's definitely going to pass that vertical line test. If we draw the vertical line, nothing is repeated, so it's certainly a function, so we can call it f of x equals. And then as far as domain and range, is the domain is how wide does it get, or what can you plug in for X and get a real answer for Y. If you're thinking about T-table, you can plug in anything for X and get any type of answer for Y. So how far does it go left to right? Negative infinity to positive infinity. Range, how far does it go up to down? And you always put the smaller number first. So the low value is negative infinity. It keeps going down, and then it keeps going up. So it's the same answer. And this is just the always answers for lines. Anytime it asks domain and range of a linear function, those are the infinities. There's no restrictions. It's the friendliest graph. It's definitely a function. And any type of value can be achieved for the X or the Y. All right, so let's think what maybe has a restriction then. For example, let's think about f of x equals the square root of x. If we try to find some points that work for this equation, and again, this just means y equals, what can we plug in for x and get a real answer for y? Now, you can plug in anything for x, but might it be an imaginary number, which would not meet the real requirement? So you can plug in a number like -1, and that's an okay answer, but it's not real. It has to be real in this section. When we're graphing, you have to be able to get a real answer for y before this is in its domain. So this is not in the domain. Neither is any negative number. You just can't plug in anything for x this time and get a real output for y. Now, you can plug in 0, the square root of 0, and check that on your calculator. That is okay. Square root of 0 is 0. You could plug in a fraction like a half. Anything positive, basically, you can plug in. Now, you might be worrying that it's not a perfect square and you get square root of 1/2, but it is real. It's not a nice real number. It is an irrational real number. You won't get a nice, even integer answer out of it. But it is real, and that's what we need. Now, what you might be thinking would be a better number to plug in might be 1. The square root of 1 comes out to those numbers we like, nice, neat numbers. And then 2, what about 2? Square root of 2, it's not one of those nice numbers, like I said, but it is real. It's about 1.4, and it'd be hard for us to graph, but it would meet the requirements that it's real. So if there is a way to graph that, you wouldn't be asked to. Another nice number, though, might be 4. Square root of 4 is 2. So you might be kind of thinking, what are these nice numbers I could plug in? And in that case, like 0, 0, I've got 1, 1, and 4, 2. Over 4, up 2. It actually makes this arc-looking shape. That's the square root function shape. So this one definitely has an abbreviated domain and range. Domain, what you can plug in for x, starts at 0. And I would use a bracket because 0 gave me a real answer. So it's included in the domain. So we would bracket that. And then it goes to the right. You know, domain means x values, the horizontal values, the left to the right. So as far as it goes to the left is at 0, then it goes to infinity, right? So we'd say to infinity. Now, actually, the range is exactly the same thing on this. The lowest it goes is also at 0, and then it's going up, not very fast, but it is going up, and over time, it just goes up higher, higher. So we'd say the range is the same on that. All right. Let's think of another one with the square root. What if it was the square root of x plus 3, y equals? This is also a function. There's no x repeated. And I should have said that on the last one. If you do the vertical line test, nothing repeats. But think about what's the first number you can plug in here. Like, can you plug in -1 on this one? Well, yeah, -1 plus 3 is 2. So square root of 2 is actually okay. You could plug in even -2 plus 3 is 1. So the square root of 1 is 1. So I can plug in some negatives this time. I could even plug in -3. -3 plus 3 is 0. The square root of 0 is 0. Well, what about -4 or anything less than -3? Now I've got trouble. So -4 plus 3, I'm into the imaginaries. So we could say the domain starts on this one at -3. Whenever you have, sometimes you have shifting rules, which we'll be talking about more later, additions or subtractions that move the domain and the range around on the graph. And then we could talk about the range of this. But this becomes an arc that's been moved back 3 places like that. All right, so we'll come back in, talk a little bit more about domain and range. So I'll see you on the next video to finish up section 2.3.